Control theory exercises. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, and in this video I would like to discuss with you 8 exercises of control theory that I selected from exams for electrical engineers. Let's go to the first exercise. Exercise number 1 says, the impulse response of an initially relaxed linear time invariant system is e raised to the power of negative 2t, u of t. The question, what would be the input to produce a response of t times e raised to the power of negative 2t u of t? Okay, my friends, this is the exercise. Let's go to the solution. The exercise gave us this, okay? And the exercise said that this is the impulse response of a initially relaxed linear time invariant system, okay? This is the output, the response. And based on this, the exercise wants us to find the input that produces this as output, okay? So this y of t equal to t times e raised to the power of negative 2t u of t is the desired response in the time domain, okay? This is what we wish. But the exercise asks us what would be the input. The exercise wants us to find the input that produces this as output, okay? This is the question. Let's go to the solution. Firstly, let's model the transfer function of the system, okay? G of S, the transfer function of the system is equal to y of S, the output in the frequency domain, divided by the input in the frequency domain. And let's call it 1 over Ts plus 1, okay? If we wish the output, we can simply do this. The output in the frequency domain is going to be equal to the transfer function times the input, okay? The output is going to be the product between the transfer function and the input. However, the exercise said that this is the response for the impulse, okay? And let's work with the impulse. The impulse in the frequency domain is equal to 1. Okay, the Laplace transform of the impulse is equal to 1. Then, if our input is the impulse, then the output is equal to the transfer function. Alright, this is the first conclusion that's going to enable us calculate everything. When the input is the impulse, the output is equal to the transfer function because the Laplace transform of the impulse is equal to 1. Okay? Therefore, when the input is the impulse, we have that the output in the frequency domain is equal to the transfer function. Alright, my friends, this is the first conclusion, and this is very important to understand and find the solution of this exercise. Now observe that the Laplace transform of E raised to the power of negative 2t is equal to 1 over s plus 2, okay? You can find it in a table. Observe that the Laplace transform of e raised to the power of negative 2t is equal to 1 over s plus 2. We find that, okay, based on this, we find that our transfer function g of s is equal to 1 over s plus 2, okay? Because we discovered that the output is equal to the transfer function when the input is the impulse. If I have this as output, then the Laplace transform of this is equal to this, and this is equal to the transfer function, okay? This is the main realization of this exercise. One more time. When the input is the impulse, the Laplace transform of the impulse is 1. Then multiplying by 1, we get this, that the output is equal to the transfer function. This is the output, and the Laplace transform of this is equal to this, and this is the output. But we found out that when the impulse is the input, the Laplace transform of the output is going to be equal to the Laplace transform of the transfer function, both in the time domain and in the frequency domain. Alright, this is the realization that we needed. And knowing that the Laplace transform of this, let's work on this now. This is the response. Let's work on this now. The Laplace transform of t times e raised to the power of negative 2t is equal to 1 over s plus 2 squared. Okay? If we wish this as a response, then then based on this realization here that we had, y of s is equal to 1 over s plus 2 squared, okay? Now returning to the transfer function, we obtain that y of s over x of s is equal to g of s. Consequently, g of what we want x of s. The exercise wants us to find the input that produces this. We want x of s. X of s is equal to y of s divided by g of s. And this is equal to 1 over s plus 2 squared times s plus 2, and this is equal to 1 over s plus 2. And as we already know that the inverse Laplace of this is this, okay, x of t equal to e raised to the power of negative 2t would produce this. So this is going to be the outcome when this is the input, okay? This is going to be the response of the system, the output, when this is the input, when the input impulse is this. Okay, my friends, and this is all for exercise 1. Let's go to exercise 2 now. Exercise number 2. The unit impulse response of a unity feedback closed loop system is y of t equal to e raised to the power of negative 2t u of t. The question, what is the open loop transfer function g of s. Okay, my friends, this is the exercise. Let's go to the solution. But before going to the solution, we need to understand what the exercise wants from us. The exercise wants g of s, the transfer function, the open loop transfer function, given that this y of t equal to e raised to the power of negative 2t u of t is the unit impulse response of a unit feedback closed loop system. Okay, the exercise gave us this and demanded us to find this. Okay, as we saw in the previous exercise, the closed loop transfer function is the Laplace transform of its given impulse response. Let's understand this. Okay, let's understand this. The Laplace transform of e raised to the power negative 2t is equal to 1 over s plus 2. Alright? This is the Laplace transform of this. This is in the time domain, this is the frequency domain. But we understood in exercise 1 that this is equal to y of s. Why? Because y of s is equal to g of s times x of s. But when the input is the impulse, its Laplace transform is equal to 1. X of s is equal to 1. Consequently, y of s is equal to g of s when the input is the impulse. Alright, my friends, this is all we need to understand. Written in terms of the open loop transfer function g of s and assuming that h of s, we are going to assume that the gain of the feedback loop is equal to 1. Okay, h of s is equal to 1. Alright, then written in terms of the open loop transfer function, we're going to write this like this. G of s open 1 plus g of s h of s. And here g of s over 1 plus g of s. As a consequence, this has to be equal to this, okay? This here is closed loop. This here is closed loop. This here is open loop. Okay? Then 1 over s plus 2 is equal to g of s over 1 plus g of s, and this leads to g of s equal to 1 over s plus 1. Okay? And this is what the exercise wanted from us. Alright? This is precisely what the exercise wanted from us. Exercise number 3 now, my friends. The step response of a system is this. Okay? This expression, this is the step response of a system. The question, what is the impulse response of this system? Okay, my friends, this is the exercise. Let's go to the solution. How do we find the impulse response of a system given its step response? The impulse response is obtained by merely differentiating the step response with respect to time. Okay, so g of t is equal to derivative with respect to time of y of t. Okay, we simply differentiate this expression here to obtain the impulse response. And if we carry out this differentiation, we find that the impulse response is 1.15 times e raised to the power of negative t times the sine of 1.73 t plus 5 minus 1.99 e raised to the power of negative t times the cosine of 1.73 times t plus 5. Okay, my friends, this is the solution of the exercise. The impulse response, the exercise gave us the step response and wanted us to find the impulse response. And the impulse response is obtained by differentiating the step response with respect to time. Okay, my friends, this is all for exercise 3. Let's go to exercise 4. Exercise number 4. A control system is defined by the following relation. This is the relation that defines this control system. The question, what is the response of the system as time goes to infinity? Okay, my friends, this is the exercise. Let's go to the solution. But firstly, let's understand the expression that the exercise provided. The forcing term has two distinct components. U of t is equal to u1 of t plus u2 of t. Alright? That is, u of t is equal to 12 minus 12 times e raised to the power of negative t. Alright? After understanding this, let's work on the characteristic equation of the system. What is the characteristic equation? The characteristic equation is this: x squared plus 6 times x plus 5 equal to 0. This is the characteristic equation whose solution is x is equal to negative 6 plus minus the square root of 36 minus 20 divided by 2. And the roots are x1 equal to negative 5 and x2 equal to negative 1. Okay? And what can we infer from this? Remember that the poles of the system are the roots of the characteristic equation. Okay? The poles are the roots of the characteristic equation, and as they are negative, alright, negative 5 and negative 1, as they are negative, the system is stable. The system is stable. Now let's consider again the forcing terms. Let's see this first. u2 of t equal to negative 12 times e raised to the power of negative t. Alright? Let's work on this. If time goes to infinity, what happens? What is going to happen there when time goes to infinity? Can you see? Do you comprehend? When time goes to infinity, this term here naturally decays to 0. Alright? So we don't need to worry about this because we know that the final value for this part here is 0. It naturally decays to 0. But how about this? u1 of t equal to 12. A step of 12 units. How about this? Does this go to 0? We don't know. We have to inspect. The Laplace transform output of the overall system due to a step of 12 units is y of s is equal to 12, the step of 12 units, divided by s squared plus 6s plus 5. Okay? We are working with this equation here. And the Laplace transform output of the overall system due to a step of 12 units is this. And how about the final value of this expression here? This is what we want. We want the final value of this expression. Y of t when t goes to infinity is equal to the limit when s goes to 0 of s y of s. And this is equal to the limit when s goes to 0 of 12 times s over s squared plus 6 times s plus 5. And if we take the limit, we get 12 over 5, which is equal to 2.4. Alright, my friends, this is the final value of the output when subjected to the aforementioned forcing terms. And this is all for exercise 4. Let's go to exercise number 5. Exercise number 5. For the system of the figure, what is the steady state error to the unit step input? Okay, my friends, this is the exercise. Let's go to the solution. The exercise gave us this block diagram and wants us to find the steady state error to the unit step input. Okay, my friends, this is what we are going to do. And let's work on the closed loop transfer function of the system. The closed loop transfer function is going to be y of s over r of s. We are relating output with input, and this is equal to g of s over 1 plus g of s h of s. This is g of s, and this is h of s. Okay? And substituting, we find this 1 over s plus 10 divided by 1 plus 1 over s plus 10 times 10. Okay? And if we work more on this expression, we find that the closed loop transfer function is equal to 1 over s squared plus 10s plus 10. Okay? This is the closed loop transfer function. The error transfer function, okay, the error transfer function can be obtained from the closed loop transfer function like this. E of s equal to r of s is equal to 1 minus y of s over r of s. And this is equal to 1 minus this. 1 minus 1 s squared plus 10 times s plus 10. Okay? And working on this, we find that it is s squared plus 10 times s plus 9 divided by s squared plus 10s plus 10. Okay, my friends, this is the E of S over R of S. We want this, we want E of S written in terms of R of S. E of S is equal to this, S squared plus 10 times S plus 9 divided by S squared plus 10 times S plus 10 times R of S. Okay? Alright? And we want to assess the error. This is the error signal, okay? This is the error signal. We want to assess the error signal when time goes to infinity, okay? The error when time goes to infinity is going to be equal to S, E of S, R of S, and this is equal to S squared plus 10s plus 9 over S squared plus 10s plus 10 1 over S. Why 1 over S? 1 over S because it is the unit step, the input is a unit step. And taking the limit, okay, because it is a limit here, it is a limit, the limit when S goes to 0, and then we find the error, and this is equal to 0.9, okay? If we take the limit of this, we find 0.9, and this is the final value, okay? This is the steady state error to the unit step input. Alright, my friends, this is all for exercise 5. Let's go to exercise 6. Exercise number 6 now. For a second order feedback system as shown in the figure, the damping ratio is 0.707 and the undamped natural frequency is 2 radians per second. Then, what are the values of K, alpha, and beta? Okay, the exercise wants this. The exercise gave us this, okay, the data, and the exercise wants us to calculate the value of K, the value of alpha, and the value of beta. Alright, my friends, this is the exercise. Let's go to the solution. Observe that the closed loop transfer function of the system is y of s over r of s is equal, this here is g of s, and this here is h of s. G of s 1 plus g of s times h of s. Okay, this is the closed loop transfer function of the system, and knowing that the g of s is this and that h of s is this, we reach that, okay, we are going to substitute in the place of g of s, we are going to put this here, and in the place of h of s, we put this. Alright? Knowing this, we find that it is equal to k over s squared plus alpha s plus 1 plus k times beta. Alright? This is the closed loop transfer function of the system. Comparing this transfer function with the standard for second order systems, we find, let's compare this with the standard for second order systems, okay, which is W n squared divided by s squared plus 2 times zeta times wn times s plus wn squared. Okay? This is our system, the system of exercise 6, and this is the standard way of writing the transfer function, the closed loop transfer function for second order systems. As the exercise stated, Wn is equal to 2 radians per second and zeta is equal to 0.707. We find that alpha is equal to 2 times zeta times Wn, which is equal to 2 times 2, okay, times zeta is 0.707, okay, zeta is 0.707, Wn is equal to 2, and this is equal to 2.828, okay. This is the first result, the value of alpha. Let's calculate now the value of beta and the value of k. The exercise wanted us to calculate the value of alpha, beta, and k. We already found alpha. Let's work on the others. Wn squared is equal to 1 plus k times b, okay? Alright, 1 plus k times beta is equal to Wn squared. Wn squared is equal to 4, okay? So k beta is equal to 3. K beta is equal to 3. But here, if you compare here with this, we find that k is equal to Wn squared, which is equal to 4. Then, we already know this. We know that alpha is equal to 2.828, k is equal to 4, and here 4 times beta is equal to 3. Beta is equal to 3 over 4, okay? This is the value of beta, 3 over 4, okay? This is what the exercise wanted us to do, to calculate the values of alpha, k, and beta. Alright, my friends, this is all for exercise number 6. Let's go to exercise number 7. Exercise number 7. What is the condition for the stability of this system here? Okay, my friends, this is the exercise. Let's go to the solution. The exercise gave us the characteristic equation of a system and wants us to use a technique to tell whether the system is stable or not and what can we do to make it stable, okay? It is possible to use Ralph's array to assess the stability of this system. This is the technique that we are going to use. We are going to use Ralph's array to assess the stability of the system. Do you know how to use Ralph's array? I'm going to show you. S to the 4th, s cubed, s squared, s to 1, and s to 0. A0, A2, A4, A1, A3, B1, B2, C1, and D1. Okay? We already know A0, A1, A2, A3, and A4. I'm gonna write them here. Observe that A0 is equal to 1, alright? A0 is equal to 1. A1 is equal to 3, okay? A1 is equal to 3. How about A2? A2 is equal to 5, okay? A3 is equal to 6, and A4 is equal to K plus 10. Okay, my friends? Alright, this is how we use Rolf's array. Now what we need to do is to calculate the values of B1, B2, C1, and D1. Alright, let's calculate B1. B1 is gonna be A1, A2 minus A0, A3 divided by A1. We simply substitute the values. We have the values here. We have A1, we have A2, A0, A3, A1. We simply substitute the values and we find that it is equal to 3. Then we write here that B1 is equal to 3, okay? Let's calculate now B2. B2 is equal to A1, A4 minus A0, A5 divided by A1. And we already have everything here. A5 is 0. A5 is 0. Then this term here is 0. Then B2 is equal to A4. And as we know the value of A4, B2 is equal to K plus 10. Alright? We calculated B1, we calculated B2. Now let's calculate C1. C1 is equal to B1, A3 minus A1, B2 divided by B1. Okay? We have the values of B1. B1 is 3, A3 is 6, A1 is 3, B2 is K plus 10, and B1 is again 3. We use the values and we find that it is equal to negative 4 minus K, okay? C1 is equal to negative 4 minus K. Alright? And lastly, we're going to find the value of D1. D1 is equal to C1 B2 minus B2 B1 times C2 divided by C1. Okay? C2 is 0, so this term here is 0. Then D1 is equal to B2. D1 is equal to K plus 10. Alright? Now that we have calculated all the entries of Rolf's array, we are going to use it to assess the stability of the system. For stability, all closed-loop poles must lie in the left half S-plane. This condition is satisfied if all entries of the first column of Rolf's array are positive, okay? All of this has to be positive. All of this has to be positive, alright? The first column of Rolf's array have to be positive. So, I know that A0 is 1, it is already positive. A1 is 3, it is already positive. B1 is 3, it is already positive. C1 is negative 4 minus K. and D1 is k plus 10. They have to be positive, okay? So this has to be greater than 0 and this has to be greater than 0, okay? They have to be positive for stability, all right? The system is going to be stable if all the closed loop poles lie at the left side of the complex plane. And Ralph's stability criterion says that all the entries of the first column have to be positive. In this way, we say that here k has to be greater than -4, and for us here k has to be greater than -10. Okay? And analyzing both results, we concluded that for stability, the final result is this: k has to be greater than -10. Alright, my friends, and this is all for exercise 7. Let's go to the last. Let's go to exercise 8. Alright, my friends, let's go to the last exercise, exercise number 8. Given a unity feedback system with g of s like this is the open loop transfer function. The question: where is the location of the dominant poles for a 30% overshoot? Okay, my friends, to find the location of the poles, we're gonna need to work with zeta and wn. Alright, let's find the zeta first, and to find the zeta, we can use the expression of the maximum overshoot. The maximum overshoot, mp, is equal to e raised to the power of negative pi zeta divided by the square root of 1 minus zeta squared, okay? And this has to be equal to 0.3 because the exercise imposed this condition, okay? It wants the location of the dominant poles for a 30% overshoot. We are going to take the natural logarithm of both sides here. Okay, taking the natural logarithm of both sides, we find that zeta is equal to 0.357. Okay, this is the value of zeta. We already know it. Okay, we found it through the expression of the maximum overshoot, 0.357. And how about the undamped natural frequency, Wn? The undamped natural frequency can be obtained using Ralph's array. Alright, we are going to use Ralph's array to obtain Wn. Consider the characteristic equation of the closed loop transfer function. This is the open loop transfer function. Let's calculate the closed loop transfer function. The closed loop transfer function, y of s over r of s is equal to g of s over 1 plus g of s, okay? We simply use this here, alright? I invite you to try that in your house and substitute this g of s here, and then we find this. K over s cubed plus 19 times s squared plus 60s plus k. Alright? This is the closed loop transfer function. And the characteristic equation is the denominator of the closed loop transfer function. This here, the denominator of the closed loop transfer function, is our characteristic equation, okay? We are going to set it to 0, s cubed plus 19 times s squared plus 60s plus k equal to 0. And we are going to use Ralph's array to calculate Wn. Ralph's array is going to be like this: s cubed, s squared, s to 1, s to 0, and here a0, a2, a1, a3, b1, and c1. Okay, my friends? And we know that A0 is 1, okay? A0, let's substitute. A0 here is 1. How about A2? How about A1? A1 is 19. A2 is 60. Let's go substituting. And A3 is K. We have to calculate the values of B1 and C1. Let's go and calculate the value of B1. B1 is going to be equal to A1, A2 minus A0, A3 divided by A1. And we substitute, and we find that it is equal to, use the values. You have to use the values. Try yourself. Do it yourself, and you're going to find that it is equal to 1140 minus K divided by 19. By making the S1 row equal to 0, we find that the K, if we make this row here equal to 0, we find that the K is equal to 1140. If I put 1140 here, this becomes 0, okay? This is one condition. In this way, it is possible to use this is the first step. Now the second step, we are going to use this here. In this way, it is possible to use the S squared row as an auxiliary equation, okay? We are going to use this here as an auxiliary equation. 19 times S plus 1140 equal to 0. And the roots are plus minus J 7.74. Okay? And now we already have the value of Wn. Okay? This is the value of Wn. Alright? We wanted to find the value of 0. We found the value of 0 using the expression of the maximum overshoot. And we found the value of the undamped natural frequency using this auxiliary equation here. And it is 7.74. Okay? With these values of zeta and Wn, we have the pair of dominant poles at, the pair of dominant poles will be at negative zeta Wn plus minus J Wn times the square root of 1 minus zeta squared. And this is equal to negative 2.76 plus minus J times 7.24. Okay? These are the locations of the dominant poles when the maximum overshoot is 30%. Okay, my friends, and this is all for this video. I hope you enjoyed it and learned from it. I am a teacher, my friends. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye.